these are the notes for target 3 within the thermodynamics unit. So the task is to compare the specific heat capacities of various substances. To start out with, we're just going to do a couple definitions, and there's also a table that if you were in class I gave to you and you glued in. If you're doing this from home, you may just want to pause me and just write this table in. It wouldn't take very long. But to start out with, the word specific in this target, when we talk about specific heat capacity, it just means that we apply it to a single substance. I'm not going to say the word specific over and over. For whatever reason, I struggle. It's like a tongue twister. So we're just going to call it heat capacity. All right, it's the same thing. You'll see it both ways. So this idea of heat capacity, think if something has a capacity, or we know it's holding something. So heat capacity refers to a substance's ability to either absorb or release thermal energy without changing its temperature. Okay, so something is able to absorb thermal energy from its environment or release it out into the environment, yet its temperature stays the same if something has a big heat capacity. And different materials have very different abilities to do this. All right, so that's one of the terms we have to get out of the way before we can move on here. Another term, we've talked about thermal energy a lot, but that's about all we've done. We've just said, you know, thermal energy is sort of like heat. When we look at thermal energy, it's the total energy of all molecules in a substance. There, finally use the whole column once we get away from that graph, or that data table. So it's the total energy of all molecules in a substance. And that's different from just saying something's hot or something's cold. Right? Because we've got a couple other words that we're going to throw out here. And one is we need to actually define temperature now. And we're going to have to define heat. Because in real life, just daily life, thermal energy and heat get used interchangeably, where in physics they're not exactly the same thing. All right. So for thermal energy, think of it this way. If you have a little ice cube, okay? We've got an ice cube, and it's small, yet we know it has thermal energy, okay? It definitely has that, so it has low thermal energy. But then, this drawing will be pretty scary, but this is an iceberg, just right at the tip of the iceberg coming out. And so still ice, but this one, we could say, has high thermal energy. That doesn't mean it's warm. It just means that there's a lot of molecules, and we know that neither of these are at absolute zero. So there's a whole lot of vibrating in place that's going on. So even you can have something that's really cold that has a lot of thermal energy if it's big enough. All right, so that's what I mean by the total energy. Now this idea of temperature, because obviously these both have a low temperature, because temperature looks at the average kinetic energy of one molecule, of a single molecule or atom. So if we looked at one water molecule, yeah, they're jiggling a little bit, but they're not going crazy. It's nothing like when we would boil water or vaporize these things. So if we look at temperature, both of these have low temps. Okay, each one would have very low temperatures. Yeah, the iceberg has a lot of thermal energy just because there's a lot of it there. So what is the difference then between heat and thermal energy? Heat is just thermal energy in transit. Okay, in transit. Okay, I have not as bad as some people in my house, but I do order probably too many things on Amazon because we have an Amazon Prime account. And so you get all these alerts that say things have shipped, things are in transit. In transit means that the energy is moving between two different things. All right, so it is moving between two objects, for example. So if you have an ice cube in your hand has thermal energy, the ice cube has thermal energy, yet when the thermal energy goes from your hand into the cube, in that little split moment of time, it's heat when it's actually moving between. All right, and it's just a technical definition. There's not a huge difference between the two, just that heat is maybe the verb, if you have any ELA nerds in here. It's the verb form of thermal energy moving between the objects. All right. Only one more quick definition, which is a calorie. And in the sand and soil heat capacity lab, we've already talked about this, but we're going to refer a lot to this table up here, and you see that the heat capacity of these substances is calories per gram of water per degree Celsius. So what that means, a calorie is the amount of energy, it's going to go capital E for energy, to raise 1 gram of water 1 degree Celsius. So remember, calorie measures energy, so it's the amount of energy that would raise 1 gram of water 1 degree Celsius. So if there were 200 calories in your breakfast this morning, that means the amount of energy in that food you ate would raise 1 gram of water by 200 degrees Celsius. All right. So if we look up here, okay, just to give some examples here, we see that water's heat capacity is 1 calorie per 1 gram per 1 degree Celsius. You have to put 1 calorie of energy into water to raise it that amount by 1 degree, to raise it by 1 degree. So if we wanted to raise the water's temperature by 5 degrees Celsius, we'd have to input 5 calories per gram. If we wanted to cool water, then water would have to release energy. If we wanted to cool a glass of water by 5 degrees Celsius, that glass of water would have to release 5 calories in order to drop the water 5 degrees Celsius. All right, so that's something that takes a little bit to wrap our head around. So if we want to look at this table, water has a really high capacity. It takes a lot of energy to make it change its temperature one way or another. A great absorption or a great release to make it change its temperature. But if you look, which of these is the lowest? The lowest heat capacity, looking for the smallest number, which is this granite or sand. Okay, so sand, we know from this table, has a low heat capacity. So if it loses 6/100ths of a calorie, it cools down by a degree. Or if it absorbs 6/100ths of a calorie, it warms up by 1 degree Celsius. All right, and that's why we've already mentioned, if you were in class, beach, which we know is sand, versus like an inland lake. I'm not talking Lake Superior that just never seems warm, but a beach, we know that when the sun comes up, it changes its temperature fast. Same thing as when the sun goes down, it cools fast. A lake, it's pretty slow. Okay, so it resists a change in temperature. And so it might warm up a little bit during the day and cool down just a little bit at night, but not very much. Okay, so we say it slowly changes temp. So that by definition then, this would have a low capacity, and the lake has a high capacity. Okay, we've also mentioned, as we did the water versus soil lab, why is it that islands, all right, there's some dream island, maybe you can discover it and name it after yourself. Okay, something towards the equator here. We're not talking an island close to the North Pole. These islands, they don't have extreme climates, all right? It's pretty stable. Okay, so not extreme. It's not like Michigan, where in January we could be 20 below zero, in July we're 100 degrees. 120 temperature swing does not happen in these places. Just think about it. If we get some cold air mass that comes over the the water is going to say, okay. It's just going to release a little bit of its warmth in there. Water temp stays about the same. And then that cold air mass isn't so cold when it goes over the island. Same thing with a super hot air mass, where, okay, here comes some, a tropical air mass, and as it goes over the water is willing to take some of that heat out of it as it's moving. So by the time it gets to the island, it's not so extreme. I mean, you're going to get some fluctuations. Yes, you're going to get, rainy seasons, monsoon, hurricane seasons. But in terms of temperatures, if you're surrounded by an ocean, even Florida, okay, a peninsula like that where you've got 3 sides surrounded, you don't see the huge swings. And we like to think in Michigan with the Great Lakes that we would see this buffering, but we don't really. All right, the Great Lakes are awesome, but they're not as big as an ocean. So it takes a large body of water to stabilize those extremes. All right, that is heat capacity, and good luck.